To continue, let me talk about some important remarks. So the first remark is the following. If A is an R5 set in Rn that contains the origin, then A is a subspace of Rn. Okay, so this property is rather obvious, and I'm going to give the proof as follows. Actually, I'm going to sketch the proof of this statement. So first of all, if we fix any x in A and any real number lambda in R, then lambda x can be written as lambda x plus 1 minus lambda times 0. Okay, so by the definition, because A is an R5 set, x belongs to A and 0 also belongs to A by the assumption. Therefore, this R5 combination belongs to A. Okay. And now, if we fix any x and y in A, then x plus y can be written as 2 times 1/2 x plus 1/2 y. Okay. By the definition of an R5 set, 1/2 x plus 1/2 y is an R5 combination of x and y. So this element belongs to A. Okay, and by this property, lambda for lambda to be 2, then lambda times this element also belongs to A. So we have proved that for any x in A and lambda in R, lambda x is in A, and for any x and y in A, we have that the sum of x plus y is in A. Therefore, A here is a subspace of Rn. Okay. The second property is as follows. This R5 set A equals, so any R5 set of Rn is closed, is a closed set, and in particular, f of omega is closed for any subset omega of Rn. Okay, so the proof of this property is also trivial. So we suppose that now obviously if the set, the R5 set, a given R5 set is empty, then this property is true obviously. So we can assume that A here is a non-empty R5 set. Okay, so then we can fix an element x0 in A. Okay, then we can build a new set as follows. Let L be the difference of A and x0. So this is the set of all elements of the form A minus X naught, where A belongs to A. Okay, so we can easily show that L here is affine, and also L belongs to and 0 belongs to L, because obviously X naught belongs to A, so X naught minus X naught is 0, so 0 belongs to L. Okay, so from here and the previous remark, we're going to see that L is a subspace of Rn. And from this representation, we can see that A is X naught plus L. Okay, and it is well known that any subspace of Rn is closed. Therefore, A here is just a translation of a closed set, and we can easily show that A is closed. Okay. The third important remark I want to mention is as follows. The sequence xk constructed in the proof of the previous theorem no, actually the previous lemma belongs to the set L equal the alpha set generated by omega, which is a subspace of Rn. Okay, so let me recall the construction of xk. Okay, so we pick x naught in the relative interior of omega, and we build xk by defining xk equal minus 1 over k times x naught. Okay, so note that we have the following assumption: 0 belongs to the closure of omega, and obviously omega is always a subset of the alpha set generated by omega. From this, we see the following: the closure of omega is a subset of the closure of the alpha set generated by omega, and as mentioned in the previous remark, this set is closed, so this is the same as the alpha set generated by omega. And note that 0 belongs to the closure of omega. So here, f of omega is an alpha set, and it contains 0. Therefore, this is a subspace of Rn. So we have proved that the alpha set generated by omega here is a subspace of Rn. Okay, and moreover, xk here is equal to minus 1 over k times x naught. Okay, so because x naught here belongs to omega, so x naught also belongs to L. Okay, so x naught belongs to L. And then this is just a constant lambda. Therefore, xk is lambda times x naught. So, because L here is a subspace, therefore xk here belongs to L. Okay. So we have proved that the sequence xk constructed in the proof of the previous lemma belongs to the alpha set generated by omega, as we can see from this figure, and L is a subspace of Rn. Okay. Okay, so let me recall the main goal of this lecture on the proof of the proper separation property. Now we want to show that omega 1 and omega 2 can be properly separated if and only if the relative interior of the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty set. Okay, so in this lemma we're gonna prove a part of this theorem, and in a particular case when the set omega 2 here is a singleton, it is the origin 0. Okay, so I'm gonna prove it in the second lemma, lemma 2. Let omega be a non-empty convex set in Rn if if 0 doesn't belong to the relative interior of omega, then omega and the singleton set 0 can be properly separated. That means there exists an element V in Rn, and over here V is non-zero such that the supremum of the inner product of V and X, where X belongs to omega, is less than or equal to the inner product of V and 0, which is 0, and also the infimum of V, the inner product of V and X, where X belongs to omega, is strictly less than the inner product of V and 0, which is also 0. Geometrically, if omega is a convex set such that 0 doesn't belong to the relative interior of omega, then we can separate the set 0 and the singleton set 0 and omega by a hyperplane L. Okay, so let me go ahead and give the detailed proof of this lemma. Okay, so the proof goes as follows. We consider two cases. Case 1. In the first case, we assume that 0 doesn't belong to the closure of omega. Okay? So we look at the case where 0 doesn't belong to the closure of omega. In this case, we proved earlier that 0 and omega can be strictly separated. Okay, so this was proved in the first lecture on a separation theorem. That means there exists a vector v non-zero such that the supremum of the inner product of v and x, where x is in omega, is strictly less than the inner product of v and the 0, which is 0. So in this case, obviously omega and 0 can be properly separated. Okay, so the proof is obvious in this case. Okay. Now let us consider the second case, where 0 belongs to the closure of omega. Okay. So in this case, zero belongs to the closure of omega, but 0 doesn't belong to the relative interior of omega by the assumption. Okay. So by lemma 1, there exists a sequence xk. This sequence xk can be chosen in L, which is the alpha set generated by the set omega, such that xk doesn't belong to the closure of omega for all k, and also xk converges to 0 as k approaches infinity. Okay. Now, before we have already proved a version of convex separation theorem in a subspace of Rn, and in this case, we look at the subspace L generated by the set omega, and we know that this set is a subspace of Rn, and we proved it in a remark written earlier. Okay, so now we look at the situation where the sequence xk here, this is omega, okay, and this is L, which is the affine set generated by omega, and xk doesn't belong to omega, so then we can strictly separate xk and the set omega by vk that is also in this subspace. Okay, so let me go ahead and write the result. Okay, so then by the separation property, the strict separation in subspaces of Rn grouped earlier there exists Vk in L, which is the alpha set generated by omega. Vk is non-zero and supremum of the inner product of Vk and x, where x runs in omega, is strictly less than the inner product of Vk and xk. Okay, so basically in this situation we see the following. This is omega and this is x naught, this is xk, so we can strictly separate xk and omega by a hyperplane defined by Vk, and we denote it by Lk. Okay, so from here we see the following. So in particular, from here we have the following property. Thus, the inner product of Vk and x is strictly less than the inner product of Vk and xk. This is true for all x in omega and k in n. Okay. So now we can divide both the sides of this inequality by the norm of Vk. Then Vk over norm Vk x, this is also strictly less than Vk over norm Vk xk, the inner product of Vk over norm Vk and xk. Okay, this is also true for all x in omega and k in n. And now we can we let Vk over the norm of Vk by Wk. Okay, then Wk is a unit vector. That means it has a norm 1. Okay, now let Wk be Vk over norm of Vk. Okay, then norm of Wk is equal to 1, and without loss of generality, we can assume that this Wk converges to some vector v, and here because the norm of Wk is equal to 1, so the norm of v is also 1. Okay, so this is based on the fact that any bounded sequence in Rn has a convergent subsequence, and then we can work with that convergent subsequence, but without loss of generality, we can assume that subsequence is just Wk. Okay, so now from here, by passing to a limit when k goes to infinity, and observe that xk here converges to 0. Okay, so then this inner product also converges to 0. Okay, so I denote this one by star. By passing to a limit in a star, we see that the inner product of V and X is less than or equal to 0 for all X in omega. Okay, so here we use an important property that the absolute value of the inner product of Wk and Xk is always less than norm of Wk times norm of Xk. And note that the norm of Wk is equal to 1, so this is equal to norm of Xk. And because Xk converges to 0, so this one converges to 0. Therefore, when we pass to a limit in here, we see that the right hand side is equal to 0, and the left hand side converges to the inner product of V and X. Okay, so we have showed that this property is satisfied. Okay, and this is the first requirement in the proper separation property of omega and 0. Okay, so what else do we have to prove? Now we have to prove the second property in the separation property of omega and 0. That means we have to show that there exists some point x bar in omega so that this inequality is strict. Okay, so it remains to show that there exists x bar in omega such that the inner product of V and x bar is strictly less than 0. Okay, so here is a very important observation, because Wk is defined by Vk over norm of Vk, and as stated earlier, Vk here, Vk belongs to L. Okay, Vk belongs to L, which is a subspace of Rn. Then Wk here also belongs to L. Okay, because we just multiply Vk by a scalar. Now, and because L is always closed, because it's a subspace of Rn, it is closed. So then Wk here converges to V, and each Wk is in L, therefore V is also in L. Okay, so observe that V is in L. Okay, so this is a very important observation, and our goal now is to show that this is true for some x bar in omega. And we're gonna go through the proof by using contradiction. Okay, so by contradiction, suppose that this is not true. Okay, suppose that this is not true. That means the inner product of V and X is always greater than or equal to 0 for all X in omega. Okay, now by this property, we have that the inner product of V and X is always less than or equal to 0 for all X in omega. Then we have the following. Then the inner product of V and X has to be 0 for all x in omega. Okay. Now we're gonna use this observation. Since v is equal to is in the set L, and remember that L is just the alpha set generated by omega. We have the following representation. V can be written as the sum of lambda I, omega I, where I runs from 1 to m. Over here, lambda I belongs to R. The sum of lambda I, where I runs from 1 to m, is equal to 1, and each omega I belongs to omega. Okay? Then, if we look at the inner product of V and itself, which is also norm of V squared, and we know earlier that V is a non-zero vector, so this is always strictly greater than 0. Okay, so over here we can write it as follows: V, the inner product of V, and the sum of lambda I, omega I, where I runs from 1 to m. Okay, and this inner product can be written as follows: it is the sum where I runs from 1 to m of the inner product of V and omega I. Okay, and here we multiply by lambda I. Okay. Now observe that the inner product of V and x is equal to 0 for all x in omega. So in particular, the inner product of V and omega I is equal to 0 because each omega I is in omega. So this sum is actually equal to 0. And this is a contradiction because norm of V squared is always strictly greater than 0. So this is a contradiction. Okay, so this contradiction shows that there exists some x bar in omega, so that the inner product of V and x bar is strictly less than 0. Okay, so we have proved that two properties are satisfied. The inner product of V and x is less than or equal to 0 for all x in omega, and the inner product of V and x bar is strictly less than 0 for some x bar in omega. Therefore, by the definition, omega and 0, the set omega and 0, can be properly separated. Now, I'm going to go ahead and prove a part of the main theorem of this section. So this is theorem 1. Let omega 1 and omega 2 be two non-empty convex set in Rn if the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty set, then omega 1 and omega 2 can be properly separated. Okay, so this part is very, very important. It gives the necessary condition for omega 1 and omega 2 to be properly separated. And later, we can also show that if omega 1 and omega 2 can be properly separated, then this intersection is also empty. Okay, so let me go ahead and prove this theorem. The proof is mainly based on lemma 2. Okay, so we define the following set. Define the set omega as omega 1 minus omega 2. Okay. Again, this is the set of all differences of elements of the form x minus y, where x is in omega 1 and y is in omega 2. Then omega is a non-empty convex set. We can prove this by using the definition of convexity of sets. And we know earlier that the relative interior of omega is equal to the relative interior of omega 1 minus the relative interior of omega 2. Since the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty set, we see that 0 doesn't belong to the relative interior of omega, which is the relative interior of omega 1 minus the relative interior of omega 2. We can show that this is true easily by a contradiction argument. If 0 belongs to this relative interior, so 0 can be written as x minus y, where x is in the relative interior of omega 1 and y is in the relative interior of omega 2. So then x is equal to y. And this element then belongs to this intersection, which is a contradiction. Okay, so by lemma 1, applied for the set omega and 0, there exists V in Rn, and V is non-zero such that the inner product of V and G is less than or equal to 0 for all Z in omega, and the inner product of V and G bar is strictly less than 0 for some G bar in omega. Okay, so from here we can show that omega 1 and omega 2 can be properly separated. And the proof goes as follows. Fix any x in omega 1 and y in omega 2. Then the element G, which is x minus y, belongs to omega 1 minus omega 2, which is omega. Thus, the inner product of Z and of V and G is less than or equal to 0 because G is an element of omega. Okay, so that means the inner product of V and x minus y is less than or equal to 0. And from here we see that the inner product of V and x is less than or equal to the inner product of V and y. Okay, so we have showed that the first property of the proper separation property is satisfied. Okay, now we can also prove that the second property is satisfied easily using this property. Okay, so since G bar belongs to omega, G bar can be written as x bar minus y bar, where x bar belongs to omega 1 and y bar belongs to omega 2. Then, as we know over here, the inner product of V and G bar is equal to the inner product of V and X bar minus the inner product of V and Y bar. And this is strictly less than 0. It follows that the inner product of V and X bar is strictly less than the inner product of V and Y bar. Okay? So this is the second property of strict separation of omega 1 and omega 2. That means we found X bar in omega 1 and Y bar in omega 2, so that V, the inner product of V and X bar, is strictly less than the inner product of V and Y bar. Therefore, omega 1 and omega 2 can be properly separated. Okay, so we have completed the proof of theorem 1. In the next lecture, I'm going to show the second part of the main theorem. That means if omega 1 and omega 2 can be if omega 1 and omega 2 can be properly separated, then the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty set.